Hello, everyone. Welcome to today's Force Media Tea Time Talk session. So today we got very special session on Iranian Interport chapter. So we got a lineup of three speakers in two different talks. Before going into the talks, I would like to introduce in my studio who we have. So we got Sara Perez and Federico Lanza, who will give me company during the session. So today we have some technical issues, but we are trying to cope up with that, and let's see how we go with that. Okay. So with this, I would like to start the session. So we got first speaker from. So his name is Arman Namai Ghasemi. I'm really sorry if I'm pronouncing it wrong. Please correct me. He's a PhD candidate in the Department of Chemical and Petroleum Engineering at Sharif University of Technology. His research area focuses on numerical modeling of two-phase flow and reactive transport inside porous media and mechanistic understanding of enhanced oil recovery or EOR by engineered water injection at the pore scale. So his talk is going to focus on post-case simulations on the fundamental aspects of low salinity water flooding. Aman, thank you very much for joining us today. I know we had some hiccups in the technicality, but Sarah and Federico managed to overcome this. And thank you for joining us today. And the floor is, or the screen is yours.
Yeah, thanks, Kemal. I would like to thank you for inviting me to this great gathering, and this is a great opportunity to share our research. And I would like to thank the Post Media Titan Talk team for giving us this opportunity, and thank you for thoughtfulness for these difficulties. And I hope the session will go as planned. Uh, okay, I would like to present you today my work, which is about full-scale simulation of the interplay between vectorability, capillary number, and salt dispersion on the efficiency of oil mobilization by low salinity water flooding and at enhanced oil recovery, which is a method for enhanced oil recovery. And I would like to thank my two professors, Dr. Shahab Aitullah and Dr. Hassan Mahani, for helping me and guiding me throughout this work. And I've always used their insights, and I would like to thank them on this platform. Okay. Uh, as an introduction, I would like to introduce you to the necessity of full-scale study in the petroleum industry. As you maybe know, that the primary levels, primary stages of oil production, uh, a considerable amount of oil remains trapped inside the reservoirs, which is a considerable amount of 60 to 70%, and this is a very high percentage. So we are trying to reduce and enhance the recovery using many different methods. Uh, this trapped oil is because of the capillary trap oil, or maybe it might be bypassed due to engineering. And one of the uh, new methods for overcoming this difficulty is using the engineered water injection method, which has an economical advantage. And it has low capital cost and operational cost, and it has been shown to be very effective. And it's a very useful method to focus on. At trying at the different scales of this effect, of this low salinity effect, uh, the industry is interested in the field scale, large scale results. But to be able to do some experiment and investigation on it, we have to focus it on inside the laboratory. So most focus has been on the ladder scale, which is inside the scale of a centimeter. But the actual mechanisms that are driving this phenomenon are happening at much lower scale inside the tiny micron scale pores of the rock where the is stored. And you can go further down to the molecular scale even and study the molecular dynamics and the behavioral forces between the substance. But the main uncertainty lies inside this intermediate scale, which is the core scale and core network scale. And we want to know how to translate this phenomena that we are observing at the molecular scale and sub-core scales to the higher scales, and so we can take advantage of them. To see and to have a very useful outcome of this low salinity water flooding technique. Compatible mechanism and cooperative mechanisms have to come together and work all together so and we can see a positive outcome of the system. As you can know, at the software scale, the detachment of oil from the rock surface has happened, and at the core network scale, this all blobs have to form a ganglion and connect to each other and have this continuity and form an oil bank at the larger scale, so that and that oil bank has to be transformed towards the a production well, so that we can see an increase in our uh, recovery. So the problem here is that how are we going to relate these observations at larger scales to the effects and phenomena that are occurring at very, very uh, smaller scales at nanometers and micrometers. With this low salinity effect that we're observing at the core scale lead to a production at higher scales. And the question is here that how to study this interplay between these several different parameters that are inside this uh, question. That these flow patterns in heterogeneous porous media that are different flow patterns we are observing at depending on the geometry of the system. And there are different dispersion regimes and salinity distribution inside the system, and the variability of the system itself is distributed. Yeah, it's not distributed uniformly. And under the flow scientific organization, you have the variability alteration also, and that changes the dynamics of the system. So we have to focus on this pore scale as a intermediary scale and study what is really going on and how what insights can we derive out of it. The approach that we used in our model is a finite volume direct numerical simulation method, and we have used the volume of fluid method, the VOF method, which is implemented inside the open source software. And the solver we have used is the intertransform form, which is openly accessible. The equations that are being solved is the mass conservation equation, momentum conservation equation, which are the Navier-Stokes single cube equations of this form, and the phase distributions to follow the evolving of the how the two phases are moving, the water phase and the oil phase. And within the water phase, we have the transport of salinity. So we can introduce the high salinity water and the low salinity water and see the outcome. The versatility alteration has been implemented by using different interpolation models for the contact angle. So the contact angle and the versatility can change between the high salinity and low salinity state. The models that we have used are seen in this figure. In most of the studies, the versatility alteration model is linear, and it changes linearly from the higher salinity to the low salinity, which is you can see in the black line is the full range interpolation salinity or the FRI. But we have implemented uh, different models. Which is the other one is the effective salinity range model. We have used in smaller range of that this salinity is changing. And there's this salinity threshold model, which the contact angle changes at a threshold. And we have implemented the time scale, which is we have introduced a near surface diffusion rate, lower. Okay. As
So,
the
Sheikh, as you can.
as a result of our uh, excuse me,
Can you
uh,
hold?
This is the geometry that we have been studying. It's a simple for a droplet model, which is consist of the smaller channel and the larger channel. And we have injected high salinity water, and we have studied the water trapping inside this geometry at different wettability states, and we can see that oil is being trapped inside the at the water at the oil wet conditions, but in the intermediate conditions and the water wet conditions, no oil will be trapped. So we have focused on these two conditions. As you can see, there is a different behavior when we have a strongly oil-wet system and the intermediate oil-wet system. At the strongly oil-wet system, by introducing the low salinity to the system, uh, capillary entry pressure starts to decrease, and we can see a formation of an oil film flow at the outlet side, and oil can gradually be produced through this oil film, and we can see a rise in the recovery because of this reduction in the intracapillary pressure, and at different models we can see different behaviors of the system, but that is mainly because the vitality is changing at different rates and at different times, and there's a delay in vitality alteration at the outside the outlet of the system, which causes this different behaviors of the system. And we can see at the linear interpolation model, it changes monotonically, and then it stops. But this is other models, because of the delay that there is in battery filtration, some of the oil gets backflowed, and the oil blob may become discontinuous, and this might cause some distortions from this recovery curve that we can see here. At the moderately oil-wet systems, uh, this oil film that I mentioned cannot be seen, and the entire oil ganglion has to be mobilized entirely. So there will be a higher time lag to reach this capillary entry pressure. Uh, but after this point is reached, the entire oil it moves all together, and we can see a sharp rise in the recovery of the system, and which is leads to a higher level of alternate recovery. You can see that most of the oil is being produced, almost all of it is produced, and uh, it seems to be a better way, but they have to be sure that this capillary entry pressure is reached. And, and if it cannot be reached for some cases, there will be no additional oil recovered, and this method will not work on this even simple model. Uh, One of the very interesting results that we observed is that the flow dynamics of the system and the state of the vitality at the outlet of the system is very important on how this uh, flow is going to change. Uh, the vitality state at the outlet of the system and at this conjunction is very important, and the shape of the interface. If it is slightly towards a more water-wet state, if this oil is mobilized, and the oil tends to enter the more wide channel, and some of the oil might backflow to the larger channel, uh, which might be a good thing, might be a bad thing in different conditions. But in this situation, there is this backflow, and now the water is pushing oil outside of the system pretty easily. At the intermediate state, using the ESR model, it is less water wet at this outlet, and less oil backflow will occur. At this stage, we have a synergy between capillary forces and viscous forces. Capillary forces are acting in the smaller channel, and the viscous forces in the larger channel, and both of them push very effectively push the oil out of the system, and we can see a high recovery. But at the ST model, when there is a delay in stability alteration at the outlet side of the system, This outlet is so oil wet that no oil will come back and have this backflow. Uh, because of this and the shape of the interface at the outlet, this synergy that I mentioned here becomes a competition. And the capillary forces in the smaller channel and the viscous forces in the larger channel have competition. And tends to break apart this oil ganglia into different smaller oil blobs, which is very detrimental for the ultimate recovery, and you have to avoid this stuff to happen. So we can see that it's not pretty easy to say what is going in the system, but just based on this simple geometry. And many different mechanisms may be involved in this problem. Uh, at the final level of our study, we have studied the interplay between dispersion rate, lethality, and capillary number. So capillary number shows how fast is flow happening in our system, and we know that inside the reservoirs, capillary number is as low as 10 to the 10 to the power of minus 6 or minus 7. But the numerical studies are being done at much higher capillary numbers, 10 to the power of minus 4 or 5, which is much higher than the reality in the reservoirs. Uh, and we cannot really go further down because of the computational time issues. But we have shown here that if we do simulation studies at higher capillary numbers, maybe the effect of this low salinity water injection cannot be fully understood and fully seen because you can see that at higher levels of capillary number, almost no effect is being observed because of this low centralization. But if we do the simulation at the lower levels, we can see that now low centralization is starting to have a really big effect and tend to improve the ultimate oil recovery very high. So this is another very important aspect to focus on in our simulation studies, and we have to focus on this lower capillary numbers. As the main conclusions of my work, I have to say that there is a synergy between the capillary forces and viscous forces which needs to be developed to ensure the connectivity of the mobilized oil. And just seeing the versatility alteration effect is not enough, and other phenomena and other patterns have to happen so that we can see this ultimate recovery. And the dispersion that was occurring in the flowing region was detrimental for the flow effect that was inside for the oil in the stagnant region. And if it's higher than a certain level, this dispersion will stop the oil and will not let higher oil to be produced, which is itself a function of geometry and the distribution inside the system. And we saw that the ST model for volatility alteration showed the highest recovery, which was because of the faster decrease in the capillary forces at the inlet side and a higher delay of the negative dispersion effect of the outlet side. As I mentioned, this lucent effect becomes much more significant at capillary numbers lower than 10 to the power of minus 5, which is also the dispersion, the power law dispersion regime. And we have seen that many complex mechanisms and responses exist even at this very simple model at this very small scale. And there is a need for more mechanistic first scale studies so that we can gain higher insights, more insights to translate them to higher scales and be used actually for reservoir scale studies. Thank you all for uh, being with me, and thanks for your attention. This is my contact info if you wanted to contact me, and I wanted to mention that the stuff that I presented today are the part of a bigger team, which is the EOR and IOR Research Center at the Sharif University of Technology, and we can see as we have studies at many different levels and many different scales, and are tending to uh, try for pilot tests and scales very soon, and which is in connection with the national oil company, and I hope all studies will be used as applications in this field. Thank you for your attention, and I'm happy to have a fruitful discussion and open to have your questions.
Okay, thank you very much, Arman, for your really, really nice presentation. I think that your work once more shows how the microscales and studied what happened in the microscales help us understand what happens at larger scales. So the interplay between the micro and the macro, again, is fundamental to understand. So we have several questions from the audience. So I will start from Marcel, who compliment with you for the very nice presentation. And a quick question: could you comment on the effect of contact angle hysteresis and the contact line pinning? Can your model include that too?
Well, at this level, no, we have not implemented our this hysteresis in our model, and we have tried to make it as simple as possible and gain as preliminary insights as possible. But yeah, it is possible to be implemented, and there is this option in inside the open form, which have we have this advancing and receding contact angles and different flow conditions. And it is a very nice topic to watch, to look at, and we are trying to implement it in our future studies, hopefully.
Okay, very good. So we have other question. Today the audience is really interested in your work. So a question from Hamed Sadeki. Very nice work. Is there any field data for comparison? So experimental data, I suppose.
Excuse me, can you repeat? I didn't
Yeah,
quite.
sure. Is there any field data for comparison, like experimental data?
Yes, field data might be relevant, but yeah, there are some experimental data that are evaluated and we have this um, checked with our model. As you can see in this slide, there wasn't time for me to show them. We have validated our model with experimental results from two aspects. The two-phase flow, the flow model itself. We have checked it with the results of the displacement inside a Conductivity model and with two regimes of inhibition and drainage. And as you can see, both results were comparable to the experimental results, and we have validated from the aspect of the low salinity effect, which is the alteration of wettability and the time scale of wettability alteration. As you can see, there is a displacement of or droplet occurring due to the low salinity by injection, and this is the black line is the experimental data from for the change in contact angle during the time. And as you can see, using different boundary conditions, we can match the time scale of the time scale of fertility alteration, the experimental data, so we can gain confidence of both our flow model and the fertility alteration model that we have somehow arrived. But I don't think there would be a possibility of validating the field scale data because there's much big gap between these scales.
Okay, very good. So there is another question from Hezan Ranae. Sorry for mispronouncing your name. Thank you, Arman, for sharing your results. With any chance, did you check if these numerical simulation results are okay? It's the same actually. Experimental achievements. Sorry, it's again the same question you already answered. So thank Hazan again for anyway for your question. So okay, if I don't know if there are other questions from the audience. So lots of people are congratulating with your nice presentation. I just have a quick question. Your entire presentation was about the effect of salinity on the system. You mentioned the distribution, low salinity, high salinity. What kind of salt? Did you have a particular kind of salt in mind during your simulation? Is the type of salt important?
Yes, actually, the type of the ions that are in the system are very important for this uh, system. And but with my study, it's just the salinity, and I haven't yet implemented the chemistry of the system inside the model, but it is the uh, rest of my PhD work, which I am working on it, and will be presenting it very soon. They have looked at the chemistry of the system and the effect of different ions at the
Mhm.
stability alteration. And the different ions work differently, and we have this potential determining ions and just non uh, involved ions. And we have to focus on ions like sulfate and calcium and magnesium. These are the most important ions, which this chemistry and this ion interactions between the water and the solid surface are determined throughout these ions. But our system for now is very simple, and it's just the total salinity of the water, just decreasing it and not studying the ion itself.
Okay. So it's left for future studies.
Yes.
Okay, very good. Okay, very good. So if there are no other questions, I would like to thank you again, Arman, for your nice presentation. And yeah, so thanks, Arman. And so we can move on for the second presentation of today. Today, the second speaker will be actually two speakers which will present jointly their work. So the speakers' name are Aysa Edayati Azar and Ali Golagay Darzi. Aysa is a Master of Philosophy graduate, while Ali is a PhD student, both from Sharif University of Technology. And today, they are going to talk about the development of a semi-analytical model considering the effects of pore water chemistry on hydraulic conductivity of clay porous matrix. So again, we will deal with a theoretical model. In this presentation, semi-analytical, and we'll study this chemical that will study this chemical effect. Okay, so Aysa and Ali, you're welcome to start your presentation.
Thank you very much. Do you have my slides?
Yes, we see your slide. Can you just put it on a full screen mode?
Yeah, thank you. Thank you, Interpol community, for giving us the opportunity to present our new achievement. Today, my friend Aysa and I are going to talk about the effects of pore water salinity on clay matrix. So our presentation has two parts. In the first part, I will talk about the unsaturated soil and specifically stable RC curves. and then Aysa will continue the presentation by focusing on saturated points of view. Salts occurs naturally within soils and water. Salinization can be caused by natural processes such as mineral weathering, gradual withdrawal of an ocean, and plants growing or landfill leachate. Bentonite is an absorbent swelling clay consisting mostly of montmorillonite. It comprises two kinds of pores, meaning macro and micro pores, as you can see in these two figures. Existing cations in soils for water could effectively change these two kinds of pores and consequently the soil's structure. Therefore, today we aim to explore the effects of salinity on some soil property like SWRC, membrane efficiency, hydraulic conductivity in the following slides. The soil water retention curve, or in the short form SWRCs, in one of the key features of unsaturated forest media that expresses the relationship between soil moisture content and suction. The rigorous characterization and modeling of this hydromechanical feature are inevitable for the investigation of slope stability, two immiscible phases flow, volumetric and shear strength behavior. Most of the existing modeling approaches have the shortcoming of ignoring the impurity of permitting aqueous fluid through for structure by simplifying it with distilled water. But the inclusion of water salinity into a reliable model cannot be denied, as a recent experimental measurement proved the significant role of fluid salinity on SWRCs, as you can see in these two figures. So increasing salt solution concentration could increase macropore size and eventually decrease the water retention capacity in a matrix suction plane, as you see in these figures. Therefore, we have proposed a new SWRC models to consider the corporate salinity influences. The model is based on well-known Van Genestein 1980 model and include one extra fitting parameters as well as three parameters of Van Genestein model. The five parameters in this model represent the osmotic suction that can be calculated using Van Hoff equations, and the side parameters is called reference suction and is used to normalize the osmotic suction in this formulation. For calibration purpose, first we should define the saturated volumetric water content, or equivalently the soil porosity, with different salt concentration. Next, we use distilled water as well as different other saline solution to determine model parameters. And finally, the model is prepared, and we can challenge its capability to predict the SWRCs for different salt concentration. At last, it is worth noting that the proposed model only considers the air intersuction variation with corporate concentration, and we are working on the model to develop and improve its capability further. Thank you all for your attention. In the next part, Aysa will continue the presentation.
Hi, do you have my screen?
Not yet, and we don't see you also. We don't have your screen yet, Aisha.
Um, any changes?
Okay, I hear you, but I didn't see your screen. Yes, now it is.
Okay. May I continue?
Yes, so please again in full screen mode and you can go on.
Okay. Um, Thank you so much. I will continue the presentation by looking at membrane efficiency and hydraulic conductivity. Membrane efficiency and hydraulic conductivity are both important parameters in clay soils. Actually, these double layers play an important role in clay behavior and make them chemically active. Clay particles actually are negatively charged, so they absorb water molecules from their positive sides, as you can see in this figure. Um, diffuse double layer. Diffuse double layer actually decrease the free space for species transport and fluid flow. As can be seen in this figure, when diffuse double layers are extremely thick or when particles are very close to each other, overlapping of diffuse double layer happens, and as a result, porous media restricts species transport. This behavior is called membrane behavior, which is quantified by a coefficient called membrane efficiency. Actually, uh, hydraulic conductivity also shows how easily water can pass through porous media. By increasing the overlapping of these diffuse double layers, we expect the amount of hydraulic conductivity to decrease and the amount of membrane efficiency to increase. As you can see in this figure, by increasing cells concentration, we will expect decrease in membrane efficiency. It happens because of the shrinkage of diffuse double layers in the clay particles, and it happens because of the effect of salt in pore water. And when we have thinner diffuse double layers, we will have more free space for species transport, and actually we have less restriction ability, and as a result, lower membrane efficiency. Um, for the rest of the presentation, we're going to talk about hydraulic conductivity, which is a very important parameter in soil as it directly affects the fluid flow and species transport. In particular, we are going to focus on bentonite-based clay layers. Generally, clays have very low hydraulic conductivity. Again, it's because of the diffuse double layers. Especially bentonite is a commercial type of clay which is full of montmorillonite minerals, which is a chemically active mineral. It means that chemical species can change their properties. For example, as you can see in this figure, by increasing salt concentration, we expect higher hydraulic conductivities. And as you can see in this picture, these changes are so significant, so we cannot ignore them. By reviewing the literature, we understood that there is no model for hydraulic conductivity actually as a function of solute concentration. And actually, since it's not always possible to measure hydraulic conductivity as a function of in laboratory, for example, and using the experimental setup, it's necessary for us to have an approximation value of that. So we took two approaches to develop a model for hydraulic conductivity as a function of salt concentration. In the first approach, we looked at the previous models for hydraulic conductivity. As you can see in this figure, actually, Champions reviewed several models for um, hydraulic conductivity of plastic soils in contact with distilled water. And as you can see, Bonipa's model et al. In 2002 has the best prediction ability compared with other models. It should be noted that this model is the revised form of a well-known Koznik-Arman model for hydraulic conductivity of soils. As it is written in this slide and in the blue box, this model is a function of void ratio and a solid density of soil and liquid limit. We use this model as a base to develop a new model for hydraulic conductivity as a function of salt concentration. Then we collected 842 data points from 9 research papers, which 44% of them were related to saline for water, and the rest were for distilled water. And we also had 92 data points for liquid limit. Liquid limit is a very important parameter for prediction of hydraulic conductivity of mainly plastic soils. As it is shown in this figure, by increasing salinity and concentration, liquid limit decreases, which is also because of the diffuse double layer and their shrinkage. These changes are more significant in lower concentration in comparison with higher concentrations. Thus, we propose the model, as you can see, a semi-logarithmic model, and then we calculate the amounts of R for each data set, and then we propose the function for R as a function of primary liquid limit, as you can see. And you can see all these data points and the curve, the fitted curve, and you can see a high R square and a perfect fit. So it's the model for liquid limit that we are going to use for our developments of hydraulic conductivity models. In the next step, the power of void ratio in the Bonin pulse model should be modified for our purpose. And as you can see in the red box, the Bonimpa et al. Assumed that this power should be a function of liquid limit. However, our data points didn't show such a trend, so we assumed that it should be a constant value, and actually it had better R score and better fit. For the rest, the power of liquid limit and the coefficient of model, CP, should be determined as well. First, we assume that the power of this liquid limit should be constant, while the figure shows deviation and low R score, as you can see. Then we insert the coupled effect of void ratio and liquid limit in the power of liquid limit, as you can see in that red box here, and it shows a better fit and a higher R square. So it's the model, the final function, the final version of model one is presented in the green box. For the rest, we are going to, I'm going to explain about the second approach. The second approach is totally based on the coupled effect of liquid limit and void ratio on each other. And we insert these coupled effect in the powers of them, as you can see in those red boxes. And you can see also the non-linear regression-based results in this 3D figure for the relationship between logarithmic form of hydraulic conductivity and also the void ratio and modified liquid limit as a function of solute concentration. In the next step, we come to verification. We collected 132 data points to verify our models. Although data points are pretty scattered, as you can see this figure, both models have fine prediction ability relatively, for example, in comparison with previous models for distilled water. Both models have fine prediction ability, and almost 90% of these data points are in the range of 1/10 to 10 times of the measured values, which is a fine estimation. And the reason behind of this high error for all kind of membrane, all kind of hydraulic conductivity measurements are related to chemical history of soil, the type of Antoinette measurement methods, and some experimental setups, last time operational error, effect of coupled phenomena, and microstructural characterization, and also compaction methodology. And actually, all these factors together were the main challenge for developing a model for hydraulic conductivity specifically. And in the last slide, we're going to look at some error evaluation. We evaluated the error using a term as it is written by logarithmic form of predicted hydraulic conductivity to measured values of that. And as you can see, these black graphs are related to Bonin-Pause model, and the red and blue ones are related respectively to model 1 and model 2. And we want to compare the performance together. First, in the figure A, we have the evaluation of errors for distilled water. The the performance of models are relatively the same for distilled water for all three models. Almost 95% of data are between 1/10 to 10 times of the measured values, as you can see. And however, when it comes to saline pull pressure, we can see the difference between the Bonimpose model and also our two newly developed models, Model 1 and Model 2. As it can be seen in figure B, predicted values are significantly less than the measured values when using Bonimpose model, while both newly developed models shows better performances. Almost 88% of these data points are in the range of 1/10 to 10 times of the measured values. And how and in the however this value is 57% of data when using a Bonimpose model. And in the figure C, we can have the error evaluation results of all data points altogether. This is water and solution also. And we can see that more Model 1 and Model 2 present somehow a uniform errors. However, Bonimpose models tend to predict values lower than their measured values. Thank you so much for your time and consideration.
Thank you very much, Ali and Alez, sir, for this nice presentation. Sorry, there was some little bit technical issues, but I'm glad everything sorted out finally here. Uh, to the audience, if you have any question, please post it in the chat box. In the meantime, I think we already got questions, so maybe I'll just read out the question from the audience first, then I ask my own question. So this first question from Hassan Mahani, who says, "A great talk and thank you. But did you measure hydraulic conductivity under stress conditions? What's the potential impact? For example, I think you did mention that the compaction ratio and stuff can change things. Would be nice to hear your thoughts on this."
Um, Actually, if I get that right, it means that there are many factors, for example, like compaction methodology and these things that have that affect the hydraulic conductivity. Actually, in these models, we try to develop a model by using just simple factors like a liquid limit and void ratio that can easily be measured. So we ignored some other factors like different stress history or, for example, compaction methodology and other factors.
Okay, thank you. I was wondering, because the different types of clay can have different impacts. You looked into only one type of clay. So, are you planning to do some more work on different clays? Because some clays can shrink, some they don't. Yeah, in water, not let's say salt, maybe not. Uh, any any plans like you want to expand, or maybe you got some thoughts on different types of clays?
Yeah, maybe in future projects, but we took just bentonite-based clays because they are very because they contain chemically active minerals. So they show the effect that we want more significantly, and that was the reason behind that. However, if we can collect more data points and more, if we had more measurements, we would have, for example, we could look at different type of clays and maybe they would show interesting results.
Thank you. I think there's one question along the same line. So, but you already mentioned things. So, there's a question from Nushan who is asking if the hydraulic conductivity in the presence of salty water is comparable with the other clays like kaolinite. But again, as you said, like there's always scope for future studies. Yep. Um,
Yeah.
okay. Any other questions from the audience? Please do type in. And if there's any question from the studio, you can post here. If I don't see any first, there's some thank you messages for the presentation. So with this, I'd like to uh, end the session, second talk session here. Thank you again, Ali and Alisa, for joining us today and accepting our invitation. Um, with this, I'll pass it on to Federico to close the session.
Thanks for Kamal. Just to conclude our session today, I would like to present you our next session planned for the 17th of May, so in 2 weeks, at 3 o'clock Central Europe time. Next time, we will deal with two different presentations. From the first from Edward Andrews from Imperial College, which will talk about the identification of the leading role of pore structure in determining recovery during low salinity water flooding. So not different from what we've seen today, actually. And the second presentation will be held by Ramin Mogadazi from Uppsala University in Sweden. And he will talk about the determination of gas remobilization and critical saturation in geological CO2 storage, from field scale observation to pore scale mechanisms. So again, the interplay between the pore scale and the macroscopic scale is important also for Ramin presentation. And after that, I would like to thank all the audience from all the Pores Media Think Tank Talks community and team. And if you're interested in presenting your topic of research, please contact us at poresmedia@gmail.com. And we are looking forward to host you in one of our next session. So please contact us and we can arrange a presentation for one of the next times. And after that, I would like to thank again all the audience, and so see you next time.